The subatomic world, where particles dance in realms too small to see, reveals a reality stranger than our senses can grasp. Quantum mechanics, the science of this unseen domain, shows us a universe where certainty fades and probabilities reign, challenging our notions of what is real. This journey into the subatomic begins with a shift in how we understand nature, a story of human curiosity unraveling truths that shape both the cosmos and our emerging technologies. The world we perceive: trees, skies, the warmth of sunlight feels solid, governed by rules we can touch and measure. A ball thrown upward arcs predictably, falling back to Earth under gravity's pull. But beneath this familiar surface lies a deeper layer, where atoms and their smaller constituents, electrons, protons, quarks, follow a different logic. Quantum mechanics, developed in the early 20th century, describes this subatomic realm, revealing behaviors that defy common sense yet underpin the reality we know. It's not a separate world with alien rules, but the foundation of our own, a hidden dance that gives rise to the tangible. The story of quantum mechanics begins with a crisis in classical physics, the framework that explained the motion of planets and the fall of apples. By the late 19th century, classical theories struggled with the subatomic. Light, thought to travel as a wave, baffled scientists when it ejected electrons from metal surfaces in the photoelectric effect. A puzzle solved by Albert Einstein in 1905. He proposed that light comes in packets, or quanta, a radical idea that earned him the Nobel Prize. Meanwhile, atoms, the building blocks of matter, posed another challenge. Ernest Rutherford, in 1911, discovered the atomic nucleus, a dense core of positive charge surrounded by electrons. But classical models failed to explain why these electrons didn't spiral inward and collapse. Niels Bohr, in 1913, offered a solution, proposing that electrons occupy specific energy levels, or orbitals, around the nucleus. Like rungs on a ladder, they could jump between levels, absorbing or emitting light, but never exist in between. This model, though incomplete, hinted at a quantized world where energy comes in discrete steps, not continuous flows. These early insights, born in the laboratories of Europe, marked the dawn of quantum mechanics, a science that would reshape our understanding of reality. The work of Einstein, Rutherford, and Bohr, among others, laid the groundwork, each step a leap into the unknown, driven by questions that refused easy answers. Teaching quantum mechanics has evolved, reflecting its growing clarity and relevance. In the 1990s, universities often taught it historically, guiding students through the confusion of its pioneers. The photoelectric effect introduced light's particle nature. Rutherford's experiments revealed the nucleus, and Bohr's orbitals explained atomic stability. This approach, while rich in context, carried the baggage of early debates, the decades of perplexity as physicists grappled with counterintuitive ideas. Students learned not just the science, but the struggle, the sense of a world turned upside down by particles that defied classical logic. Today, the approach has shifted, a change driven by the need for clarity in a world increasingly shaped by quantum technologies. Modern courses often start with the theory as we understand it now, presenting quantum mechanics not as a historical puzzle, but as a precise description of nature. The focus is on fundamental concepts, like the property of particles called spin, which encapsulates the strangeness of the subatomic. Spin is not a literal rotation, but a quantum trait, like a coin that can be heads or tails. Unlike a classical coin, a quantum particle, such as an electron, can exist in a superposition, a state where it is both heads and tails, or any mixture, until measured. This is the heart of quantum mechanics, a reality where outcomes are not fixed, but probabilistic. The shift in teaching reflects a deeper truth. Quantum mechanics is not a theory of confusion, but of precision. The probabilities it predicts are not due to ignorance, as in weather forecasts where we lack full data about clouds and winds. Instead, they are intrinsic, woven into the fabric of nature. An electron's spin, for instance, might be 50% up and 50% down, not because we don't know its state, but because that mixture is its state. This fundamental uncertainty, explored by physicists like Werner Heisenberg and Erwin Schrödinger in the 1920s, is not a flaw, but a feature, a defining aspect of the subatomic world that shapes the universe we see. The human connection to this science is profound. We live in a world of solid objects, yet our reality emerges from the subatomic, where particles blur between states, defying our intuition. Quantum mechanics challenges us to rethink existence, to see the cosmos not as a machine, but as a tapestry of probabilities. The pioneers, Einstein, Bohr, Heisenberg, were not just scientists, but seekers, wrestling with questions that touched the nature of reality itself. Their debates, often heated, reveal a human struggle to grasp the ungraspable, a quest that continues today as we probe the subatomic with new tools and ideas. The melancholic beauty of quantum mechanics lies in its duality. It offers precise predictions, guiding technologies like quantum computers, yet leaves us with mysteries about what it all means. The subatomic world, so alien in its behavior, is the foundation of our own, a reminder that the familiar is built on the strange. This tension between certainty and uncertainty, between the seen and the unseen, mirrors our own existence, fleeting yet curious, always reaching for truths just beyond our grasp. The shift in teaching quantum mechanics, from historical confusion to modern clarity, reflects this journey, a move from grappling with the unknown to embracing its rules. The relevance of quantum mechanics extends beyond theory. In the 20th century, it was a scientific frontier, its implications philosophical. Today, it drives innovation, with quantum technologies harnessing subatomic behavior. Quantum computers, built on qubits that exploit superposition, promise calculations beyond classical limits, solving problems in chemistry and cryptography that would take eons otherwise. These technologies, emerging in the 21st century, make the subatomic world tangible, transforming abstract probabilities into tools that shape our lives. The work of companies like Google and IBM, investing in quantum devices, underscores this shift, a bridge from the microscopic to the practical. This narrative of the subatomic world is just beginning. The concepts of spin and superposition, so central to quantum mechanics, are the first steps in a deeper exploration. The universe, from its smallest particles to its grandest structures, is governed by these rules, and our understanding of them is evolving. The story of quantum mechanics is one of human persistence, of minds seeking to unravel the cosmos's secrets, even as those secrets challenge our deepest assumptions. As we move forward, we'll delve into the experiments and phenomena that define this strange reality, each a window into a universe more complex and wondrous than we ever imagined. The subatomic world defies our instincts, revealing particles that act as both points and waves, blurring the line between certainty and possibility. The double-slit experiment, a cornerstone of quantum mechanics, captures this strangeness, showing how electrons explore multiple paths at once, challenging our view of reality. This exploration into the quantum realm unveils a universe where the act of observation shapes what is, a dance of probabilities that echoes through our technologies and our understanding of existence. Quantum mechanics, the science of the subatomic, moves us beyond the familiar, where objects follow predictable paths. In the early 20th century, physicists uncovered a reality where particles like electrons behave in ways that defy classical logic. The concept of superposition, where a particle can exist in multiple states simultaneously, hints at this strangeness, but it's the double-slit experiment that brings it into sharp focus, described with unmatched clarity by Richard Feynman in his 1965 lectures. This experiment is a window into the quantum world, a simple setup that reveals the profound complexity of nature's smallest scales. Imagine an electron gun, a device that fires electrons one at a time, aimed at a barrier with two narrow slits. Beyond the barrier lies a screen, ready to record where each electron lands. In a classical world, we'd expect electrons to behave like tiny bullets, passing through one slit or the other, creating two clusters of hits on the screen, one opposite each slit. A bit of scattering might blur the edges, but the pattern would be straightforward, most electrons landing directly behind the slits, with fewer in between. This is how marbles or grains of sand would behave, each choosing a single path based on its trajectory. But electrons tell a different story. When both slits are open, the screen shows not two clusters, but a series of stripes, bright bands where many electrons land, separated by dark gaps where few or none appear. This is an interference pattern, the hallmark of waves. Water waves passing through two slits create similar stripes, as peaks from one slit reinforce peaks from the other, and peaks cancel troughs, producing areas of high and low intensity. Light, known since the 19th century to exhibit wave-like behavior, produces this pattern too. As Thomas Young demonstrated in 1801, the surprise is that electrons, thought to be particles, mimic this wave-like dance, suggesting they spread out, passing through both slits to interfere with themselves. The experiment grows stranger when electrons are fired one at a time. Classical intuition suggests each electron must choose one slit, building the two-cluster pattern over time. Yet, even singly, electrons form the same striped interference pattern, as if each particle explores both slits simultaneously. This defies the idea of a definite path, implying that an electron, in some sense, exists as a wave of possibilities until it hits the screen. Feynman's lectures, freely available and widely praised, emphasize this: the electron does not choose one slit but navigates all possible routes, its behavior governed by probabilities that combine to shape the outcome. To understand this, quantum mechanics uses a mathematical tool: complex numbers. Each possible path an electron can take from gun to slit to screen is assigned a complex number, pictured as a clock hand with a length and angle. The angle, or phase, shifts as the electron travels, like a clock ticking at different speeds along each route. At the screen, the complex numbers for all paths to a given point are added together, their clock hands aligning or canceling based on their angles. The resulting length, squared, gives the probability of finding the electron at that point. Where clock hands reinforce, the probability is high, creating bright stripes. Where they cancel, it's low, forming dark gaps. This calculation, simple yet powerful, predicts the interference pattern with precision. This wave-particle duality is not a trick, but a fundamental truth. Electrons are neither particles nor waves, but entities that exhibit both natures, depending on how we observe them. The double-slit experiment shows that an electron's path is not fixed until measured. Its possibilities spread across space like a wave. If we place detectors at the slits to see which one the electron passes through, the interference pattern vanishes, replaced by two clusters, as if the act of observation forces the electron to choose. This collapse of possibilities, central to quantum mechanics, suggests that reality at the subatomic level is shaped by interaction, a concept that challenges our classical view of an objective world. The human connection to this experiment is profound. We live in a world of solid objects, where choices seem clear left or right, here or there. The double-slit experiment upends this, showing a reality where paths blur, where a single particle explores all possibilities until seen. This strangeness, first glimpsed by physicists like Max Born and Werner Heisenberg in the 1920s, sparked debates that continue today, as we grapple with what it means for nature to be inherently probabilistic. The experiment is not just a scientific milestone, but a mirror to our own limits, a reminder that the universe's deepest truths lie beyond our everyday experience. The melancholic beauty of the double-slit experiment lies in its revelation of a hidden world. The bright stripes on the screen, formed by countless electrons, are a testament to nature's complexity, a pattern born from the interplay of unseen possibilities. Yet there is a quiet sadness in its implications, a recognition that reality, at its core, eludes our grasp. The electrons dance through both slits. Its wave-like spread is a fleeting moment, collapsing into a single point when we look. This interplay of freedom and constraint, of possibility and certainty, echoes our own existence, where choices shape outcomes in ways we cannot fully predict. The scientific foundation of the experiment is robust, grounded in decades of observation. Since its inception in the early 20th century, the double-slit experiment has been repeated with electrons, photons, and even molecules, each confirming the interference pattern. Feynman's 1965 description, in the third volume of his lectures, remains a gold standard, praised for its clarity and depth. The mathematics of complex numbers, developed by Born and others, provides a precise tool, predicting outcomes with accuracy that underpins modern quantum technologies. The experiment's simplicity. Gun? Slits. Screen belies its power, encapsulating the core of quantum mechanics in a single setup. The experiment also bridges the subatomic and the tangible. Quantum mechanics, once a theoretical curiosity, now drives innovation. The wave-like behavior of particles, seen in the double-slit pattern, informs technologies like electron microscopes, which rely on electrons' wave properties to image the nanoscale. This connection to the practical, to tools that shape our world, makes the experiment more than an abstract puzzle. It's a key to understanding how the subatomic shapes the reality we touch. The work of companies building quantum devices, inspired by such phenomena, underscores this relevance, a thread that will weave into the cosmos's broader story. This narrative of the subatomic world deepens our journey. The double-slit experiment, with its stripe patterns and wave-particle duality, is a gateway to quantum mechanics strangeness, a step beyond the foundational concepts of spin and superposition. The universe, from its smallest particles to its grandest structures, is shaped by these probabilities, and our exploration is far from over. The story of quantum mechanics is one of human persistence, of minds probing the unseen. Each discovery a light in the darkness of the unknown, leading us toward truths that challenge and inspire. Quantum mechanics unveils a subatomic world where particles exist in multiple states at once, their fates governed not by certainty, but by intrinsic probabilities. This principle of superposition, where an electron can be both here and there until observed, reveals a reality far stranger than our everyday experience. As we delve deeper into this quantum realm, we uncover a universe where chance is woven into its fabric, a tapestry of possibilities that challenges our understanding and shapes the technologies transforming our lives. The double-slit experiment, with its striped patterns of electrons acting like waves, opened a window into the quantum world, showing particles navigating all paths at once. This wave-particle duality hinted at a reality where classical notions of fixed trajectories fail. Superposition takes this strangeness further, defining a state where a particle, like an electron, can embody multiple possibilities simultaneously, unlike a coin toss, where heads or tails is determined but unknown. A quantum particle in superposition is genuinely both states say, spin up and spin down until a measurement forces a single outcome. This concept, central to quantum mechanics since its formalization in the 1920s, is not a quirk, but a cornerstone, revealing the subatomic world's fluid nature. Superposition is often illustrated with a simple analogy, a quantum coin. A classical coin, flipped in the air, lands as heads or tails, its state fixed even if hidden. A quantum coin, however, can exist in a blend of both, perhaps 40% heads and 60% tails, or any combination. This blend, or superposition, is not a guess based on incomplete knowledge, but a precise description of the particle's state. An electron's spin, for instance, might be a mix of up and down, its reality a superposition until measured, when it snaps to one or the other. This behavior, first articulated by physicists like Werner Heisenberg and Erwin Schrödinger, defies our intuition, suggesting a world where possibilities coexist until observed. The probabilities in quantum mechanics are not like those in everyday life. When we say there's a 50% chance of rain, we're expressing uncertainty due to limited data cloud positions, wind patterns, humidity. With enough information, we could predict the weather exactly. Quantum probabilities, however, are intrinsic, not a reflection of ignorance, but a fundamental property of nature. An electron in superposition isn't up or down waiting to be revealed. Its state is a mixture, and the probabilities say 70% up, 30% down are encoded in its quantum description. This insight, developed through the work of Max Born in 1926, transformed physics, showing that chance is not a flaw, but a feature of the subatomic world. This intrinsic uncertainty is what makes quantum mechanics so counterintuitive. In the classical world, we assume objects have definite properties, even if unmeasured. A ball is in one place, moving at one speed, whether we see it or not. Quantum mechanics upends this, suggesting that unmeasured particles lack fixed states. An electron's position or spin exists as a spread of possibilities, described by a mathematical wave function that evolves until a measurement collapses it into a single outcome. This collapse, a mystery still debated today, hints at a reality where observation plays a role, a concept that has puzzled scientists since the 1930s. The human connection to superposition is both humbling and exhilarating. We navigate a world of solid choices left or right, now or later, yet the subatomic realm reveals a fluidity we cannot touch. Superposition challenges us to rethink reality, to see the universe as a canvas of possibilities, not certainties. The physicists who shaped this theory, Heisenberg, Schrödinger, Born, were not just calculating but questioning, their minds stretched by a world where particles defy singular states. Their struggle, a deeply human endeavor, mirrors our own quest for meaning in a reality that resists easy answers, a pursuit that binds us to the cosmos's mysteries. The melancholic beauty of superposition lies in its ephemeral nature. An electron's blend of states, a delicate balance of up and down, exists only until measured, its possibilities collapsing into a single truth. This fleeting multiplicity, where all outcomes coexist, is a poetic reflection of life's own uncertainties, where choices hover until decisions are made. The quantum world, so precise in its mathematics, is also transient, its states dissolving under scrutiny, a reminder that even the universe's deepest truths are fragile, shaped by the act of looking. The scientific foundation of superposition is robust, built on decades of experiment and theory. Schrödinger's 1926 wave equation formalized the wave function, a tool that describes a particle's superposition and predicts its behavior. Born's interpretation, linking the wave function's amplitude to probability, gave quantum mechanics its predictive power, validated by countless experiments. The 1957 work of Everett introduced the many worlds interpretation, suggesting that all possible outcomes of a superposition occur in parallel realities. Though this remains controversial, these ideas, grounded in mathematics, underpin our understanding, from atomic spectra to modern quantum devices. Superposition's relevance extends beyond theory, touching the technologies that define our era. Quantum computers, emerging in the 21st century, rely on qubits, quantum bits that exploit superposition to exist in multiple states at once. Unlike classical bits, which are 0 or 1, a qubit's superposition allows it to represent both simultaneously, enabling computations that classical computers cannot match. This power, harnessed by companies like IBM and Google, stems from the subatomic world's probabilistic nature, making superposition not just a scientific curiosity, but a practical force, a bridge from the microscopic to the transformative. The implications of superposition stretch across scales, from atoms to the cosmos. The early universe, a soup of particles, was shaped by quantum fluctuations, tiny superpositions that seeded galaxies. Today, these principles guide our tools, from lasers to MRI machines, each a testament to the subatomic's reach. The work of physicists, past and present, reflects a relentless pursuit of clarity, a drive to map the unseen with equations that capture its essence. Their discoveries, from Born's probabilities to Everett's bold theories, are not just science, but stories, each a step toward understanding a reality that blends order and chance. This narrative of the subatomic world deepens our exploration. Superposition, with its intrinsic probabilities, builds on the double-slit experiment's revelations, showing a universe where particles live in a state of becoming. The cosmos, from its smallest fragments to its grandest arcs, is governed by these rules, and our journey is far from over. The story of quantum mechanics is one of human tenacity, of minds seeking truths that shimmer just beyond reach, each insight a spark in the vast darkness of the unknown, leading us toward a deeper grasp of reality's strangest layers. Quantum entanglement binds particles across vast distances, their fates intertwined in ways that defy our classical understanding, revealing a subatomic world where connections transcend space. This phenomenon, where measuring one particle instantly shapes another's state, challenges our notions of reality and locality, offering a glimpse into the universe's deepest unity. As we explore entanglement, we uncover a cosmos where the smallest entities share invisible threads, a profound mystery that fuels both scientific discovery and our quest for meaning. The subatomic world, unveiled through quantum mechanics, has shown us particles that exist in multiple states and navigate all paths at once. Superposition allows an electron to be both up and down, while the double-slit experiment reveals its wave-like dance through dual slits. Entanglement takes this strangeness further, linking particles so their properties are not independent but correlated, no matter how far apart. This phenomenon, first proposed in the 1930s, is not just a quirk but a cornerstone of quantum mechanics, reshaping our view of the universe's interconnectedness. Entanglement arises when two or more particles interact, their quantum states becoming inseparable. Consider two electrons, each with a spin that can be up or down. In an entangled state, such as a Bell state, their spins are linked. If one is up, the other must be down, and vice versa. This correlation holds even if the electrons are separated by vast distances, say, one on Earth and the other near Pluto. Measuring the spin of one electron instantly determines the other's, a connection that seems to defy the speed of light. This puzzled early physicists, including Albert Einstein, who, in 1935, co-authored a paper with Boris Podolsky and Nathan Rosen, calling it spooky action at a distance and questioning quantum mechanics' completeness. Einstein's skepticism stemmed from a belief in locality, the idea that objects are only influenced by their immediate surroundings. In classical physics, information travels no faster than light, so distant objects cannot affect each other instantly. Entanglement appeared to violate this, suggesting a hidden reality where particle states are predetermined, not truly quantum. This debate, known as the EPR paradox after its authors, sparked decades of inquiry. In 1964, John Bell proposed a mathematical test, Bell's inequalities, to distinguish between quantum entanglement and classical hidden variables. Experiments since the 1970s, culminating in a 2022 Nobel Prize for Alain Aspect. John Clauser and Anton Zeilinger confirmed quantum mechanics predictions, showing entanglement's correlations are stronger than classical physics allows. The mechanics of entanglement are precise, rooted in the quantum wave function. When two particles entangle, their individual wave functions merge into a single, shared state. For a Bell state, the system is described as a superposition of up-down plus down-up, meaning the pair's total state is fixed, but individual spins are undefined until measured. Measuring one electron spin, say, finding it up collapses the shared wave function, instantly setting the other to down, regardless of distance. This collapse, a quantum mystery, does not transmit information faster than light, preserving relativity, but it implies a deeper connection, a non-locality where the universe's parts are more intertwined than we thought. The human connection to entanglement is both awe-inspiring and disquieting. We live in a world of separate objects, where actions here don't instantly affect there. Entanglement challenges this, suggesting a universe where distant particles share a bond, their fates linked by invisible threads. This idea, first debated by Einstein and his peers, resonates with our longing for connection, for a reality where the cosmos is not fragmented but whole. The physicists who tested Bell's inequalities, risking careers on delicate experiments, embody this human drive, their work a testament to our need to probe the unknown, even when it defies our instincts. The melancholic beauty of entanglement lies in its fleeting intimacy. Two entangled electrons, sharing a single quantum state, are bound across space, yet a single measurement severs their link, collapsing their shared reality into separate truths. This transient unity, where particles are one until observed, mirrors our own connections, moments of closeness that fade with time or choice. The quantum world, so precise in its predictions, is also fragile, its bonds dissolving under scrutiny. A poignant reminder that even the universe's deepest ties are ephemeral, shaped by the act of seeing. The scientific foundation of entanglement is robust, validated by rigorous experiments. Bell's inequalities, tested with photons and electrons, show correlations that classical physics cannot explain, confirming entanglement's reality. Aspect's 1982 experiments, using polarized photons, demonstrated that entangled pairs violate classical limits, a result replicated with increasing precision. The 2022 Nobel Prize recognized this, affirming entanglement's role in quantum mechanics. These findings, grounded in mathematics and observation, underpin technologies like quantum cryptography, where entangled particles secure communications, and quantum teleportation, where states are transferred across distances. Entanglement's implications stretch beyond the lab, touching the cosmos itself. In the early universe, particles entangled during the Big Bang may still share correlations, their states linked across billions of light years. Black holes, probed by theorists like Juan Maldacena, may involve entanglement, with their interiors tied to distant radiation via quantum connections. These ideas, explored in the 21st century, suggest entanglement is not just a subatomic curiosity, but a universal principle, weaving the cosmos's fabric from stars to quarks. The work of researchers, from Bell to Zeilinger, reflects a relentless pursuit. Each experiment a step toward a reality that binds the smallest scales to the grandest. The practical impact of entanglement is growing. Quantum technologies, emerging in the 21st century, harness entangled states for unprecedented capabilities. Quantum key distribution, used in secure networks, relies on entangled photons to detect eavesdroppers, ensuring unbreakable encryption. Companies like Microsoft and Amazon, investing in quantum systems, see entanglement as a key to future computing, where correlated qubits solve problems beyond classical reach. These applications, rooted in the subatomic, make entanglement tangible, a bridge from the microscopic to the transformative, shaping our world in ways once thought impossible. The human story of entanglement is one of persistence and wonder. The EPR paper, born in 1935, sparked a debate that spanned decades, from smoky seminar rooms to high-tech labs. The physicists who chased this mystery bell crafting inequalities. Aspect-aligning lasers were not just solving equations, but seeking truth. Their work a dialogue with the cosmos. Their discoveries, often met with skepticism, reveal a human spirit unafraid of the strange, a drive to connect the seen with the unseen, to find unity in a universe that seems divided. This narrative of the subatomic world deepens our journey. Entanglement, with its invisible bonds, builds on the revelations of superposition and the double-slit experiment, showing a universe where particles are not solitary, but linked. The cosmos, from its smallest fragments to its grandest arcs, is shaped by these connections, and our exploration continues. The story of quantum mechanics is one of human curiosity, of minds unraveling truths that shimmer just beyond reach. Each insight a spark leading us toward a reality where the universe's deepest mysteries await. The subatomic world, a realm of probabilities and unseen connections, shapes our reality through quantum mechanics, a science that powers transformative technologies and probes the nature of existence itself. Quantum computing, harnessing the strange behaviors of particles, promises to redefine our capabilities, while the philosophical questions of quantum reality challenge our understanding of truth. This journey, from the subatomic to the cosmic, reflects humanity's quest to unravel the universe's mysteries, a narrative of wonder and uncertainty that binds us to the infinite. Our exploration began with the foundations of quantum mechanics, where particles defy classical rules, existing in multiple states and navigating all paths. The double-slit experiment revealed electrons as both particles and waves, their interference patterns a testament to quantum strangeness. Superposition showed particles in blended states, their fates governed by intrinsic probabilities, not ignorance. Entanglement linked distant particles, their states intertwined across space, suggesting a universe more unified than we imagined. Now we turn to quantum computing, a technology that leverages these principles and the philosophical debates that question what quantum mechanics reveals about reality, concluding a narrative that spans the smallest scales to the grandest inquiries. Quantum computing, emerging in the 21st century, transforms the subatomic world's peculiarities into practical power, unlike classical computers, which use bits as zeros or ones. Quantum computers employ qubits, quantum bits that exploit superposition to exist as both 0 and 1 simultaneously. This allows a qubit to represent multiple states at once, a property amplified when multiple qubits are entangled, their states correlated to form a vast web of possibilities. A classical computer with 100 bits has one of 2 to the 100th power configurations at a time. But 100 entangled qubits can represent all 2 to the 100th power configurations simultaneously, a number exceeding the atoms in the observable universe. This computational power stems from the subatomic behaviors we've explored. Superposition, seen in electrons' blended spins, lets qubits explore multiple solutions concurrently. Entanglement, binding particles across distances, enables qubits to share states, enhancing calculations. The double-slit experiment's wave-like interference inspires quantum algorithms, where possibilities reinforce or cancel, guiding solutions. Companies like Google, Microsoft, and IBM. Investing in quantum computers since the 2010s aimed to solve problems beyond classical reach, optimizing chemical reactions, cracking encryption, modeling complex systems by harnessing these quantum traits, turning the subatomic into a tool for human progress. Yet, quantum computing is not just a technological leap, but a bridge to the philosophical. Quantum mechanics, since its inception in the 1920s, has sparked debates about reality's nature, the theory's predictions, interference patterns. Entangled correlations are precise, validated by experiments from the double-slit to Bell's inequalities. But its interpretation, what it says about existence, remains contentious. The Copenhagen interpretation, favored by Niels Bohr, posits that a particle's state is undefined until measured, reality shaped by observation. Hugh Everett's 1957 Many Worlds interpretation suggests every measurement spawns parallel universes, each realizing a different outcome. These views, still debated, reflect attention: is reality objective, or does it depend on us? The philosophical implications deepen with quantum computing. A quantum computer, manipulating thousands of entangled qubits, operates in a space of possibilities far beyond human intuition. Its calculations, leveraging superposition and entanglement, suggest a reality where countless states coexist, a computational multiverse within a single device. This raises questions if a quantum computer explores all paths. What does this say about the universe's structure? The work of physicists like David Deutsch, who in 1985 proposed quantum computing's theoretical framework, frames it as evidence for many worlds, where each calculation reflects a branching reality. Others, like Chris Fuchs, advocate cubism, arguing quantum states reflect our knowledge, not objective truth, a view that questions the cosmos's independence. The human connection to these questions is profound. We are beings of classical intuition, seeing the world in fixed states here or there, now or then. Yet quantum mechanics reveals a fluid reality, where particles blur and connect across space. This challenges our sense of self, our place in a universe that may be probabilistic, observer-dependent, or infinitely branched. The physicists who shaped quantum mechanics bore debating Einstein. Bell crafting inequalities were not just scientists, but philosophers, their questions echoing our own search for meaning. Their legacy, carried by today's researchers building quantum machines, is a human story, one of curiosity pushing against the unknown, seeking truths that shimmer just beyond reach. The melancholic beauty of quantum mechanics lies in its unresolved mysteries. The subatomic world, so precise in its predictions, leaves us with questions about what lies beneath. Superposition's fleeting possibilities, entanglement's fragile bonds, and computing's vast potential are transient, collapsing into certainty when measured, mirroring life's own impermanence, moments of choice that fade into decisions. The universe, woven from quantum threads, is both eternal and ephemeral, its truths enduring yet elusive, a poignant reflection of our own fleeting existence, where wonder persists despite uncertainty. The scientific foundation of quantum computing is robust, building on decades of quantum mechanics. Richard Feynman's 1982 proposal for quantum simulation laid the groundwork, showing qubits could model complex systems efficiently. Peter Shor's 1994 algorithm for factoring large numbers demonstrated quantum computers' potential to break classical encryption, sparking global investment. Recent advances, like Google's 2019 claim of quantum supremacy, show machines solving problems classical computers cannot, though practical quantum computers, with thousands of stable qubits, remain a challenge. These developments, rooted in superposition and entanglement, affirm the article's emphasis on quantum technology's transformative power. The broader impact of the subatomic world extends across scales. Quantum mechanics governs atoms, shaping chemistry and life, and the early universe, where fluctuations seeded galaxies. Its technologies, lasers, semiconductors, MRI machines touch our daily lives, while quantum computing promises to solve cosmic mysteries. From black hole dynamics to protein folding, the article's focus on quantum's practical relevance from the 1990s to today underscores this. A thread woven through our narrative, the work of companies like IBU, scaling quantum systems, reflects a global effort connecting the subatomic to human ambition, from microscopic qubits to macroscopic dreams. Reflecting on this narrative, we see a journey through the subatomic world's strangeness. It began with quantum mechanics foundations, where Bohr and Einstein probed atoms' secrets. The double-slit experiment unveiled wave-particle duality, showing particles' dual nature. Superposition revealed intrinsic probabilities, a reality of blended states. Entanglement bound particles across space, suggesting cosmic unity. Now, quantum computing and philosophical debates tie these threads, showing a universe where the subatomic shapes both technology and thought. This arc, spanning a century, is a testament to human persistence, each discovery a light in the quantum darkness. The philosophical questions linger, a quiet echo of our exploration. Is reality a single truth, or a tapestry of possibilities? Does observation create the cosmos, or merely reveal it? These debates, from Copenhagen to many worlds, reflect our struggle to grasp a universe that defies intuition. Quantum computing, with its qubits dancing in superposition, amplifies this, a machine that mirrors the cosmos's complexity. The article's call to understand quantum mechanics, not as abstract but as vital, resonates here, a reminder that the subatomic is not distant but foundational, shaping our world and our questions. The human perspective is central. We are fleeting beings, yet we probe the eternal, our minds reaching from atoms to stars. The subatomic world, so alien, is ours. Its probabilities the root of our reality. The physicists who built quantum mechanics, from Schrödinger's equations to Aspect's experiments, were seekers. Their legacy a call to wonder. We, too, are part of this story. Our technologies and questions a bridge to the cosmos, a defiance of the unknown that gives our brief existence meaning. As we conclude, we carry this wonder forward. The subatomic world, from its strange behaviors to its technological promise, is a human narrative, one of resilience and curiosity. It began with atoms, grew through experiments and theories, and now shapes our future, from qubits to cosmic truths. The universe, vast and probabilistic, is a testament to possibility. Its mysteries waiting in the quantum weave. We are its witnesses, our questions echoing in a reality that blends chance and connection, a quiet vow to keep chasing the truths that lie beyond the edge of the known.
Imagine a world where every decision, every chance event splits the universe into countless parallel realities. Each choice you make, no matter how small or insignificant it may seem, creates a new branch in the vast tree of existence. Picture yourself facing a life-threatening situation. In one universe you might not make it, but in another, you survive against all odds. Now, envision a reality where you always survive, branching off into a new universe each time you escape death. This means that for every perilous moment, there's a version of you that continues to live on. This captivating and somewhat unsettling concept is known as quantum immortality. It challenges our understanding of life and death, suggesting that consciousness might never truly end. It stems from the mind-boggling realm of quantum mechanics, the theory governing the universe at its smallest scales. Quantum mechanics reveals a world where particles can exist in multiple states at once, only settling into a single state when observed. Quantum immortality takes inspiration from a particular interpretation of this theory, the many-worlds interpretation, or MWI. This interpretation posits that all possible outcomes of a quantum event actually occur, each in its own separate universe. This interpretation suggests that every quantum event causes reality to split into multiple parallel universes. Each new universe is a reflection of the different possible outcomes of that event. Each split creates a new universe identical to the original up until the point of the split. From that moment on, each universe follows its own unique path shaped by the different choices and events that unfold. Could this mean that somewhere in a parallel universe, there's a version of you who has cheated death time and time again? A version of you who continues to live on, experiencing new adventures and challenges in an endless array of realities? The intriguing idea of quantum immortality. Quantum immortality at its core proposes a radical idea. Consciousness never truly experiences death. This concept is rooted in the many worlds interpretation of quantum mechanics, which suggests that all possible outcomes of a quantum event actually occur, each in its own separate universe. Instead, in any scenario where death is a possibility, our awareness shifts to a parallel universe where we survive. Consider a car accident. In one universe the crash might be fatal, but in another you might walk away without a scratch. In most universes you might emerge unscathed or with minor injuries. The idea is that your consciousness continues in the universe where you survive, no matter how improbable that survival might be. However, in a few, the accident could be fatal, but according to quantum immortality, you would never experience those fatal outcomes. Your consciousness would always find a way to persist. According to quantum immortality, your consciousness would simply continue in a universe where the accident wasn't fatal. This means that, from your perspective, you are effectively immortal. This continuous branching of universes applies to every quantum event, every moment of our lives. Every decision we make, every action we take, creates a new branch in the multiverse. With each tick of the clock, countless new universes are born, each representing a different outcome. This means that there are infinite versions of you, each living out a different possibility. This implies an infinite number of yous, each experiencing a unique trajectory through the vast multiverse. The concept of quantum immortality challenges our understanding of life and death, suggesting that our consciousness might be far more resilient than we ever imagined. To grasp the essence of quantum immortality, we need to delve into the heart of quantum mechanics and the many worlds interpretation. This interpretation challenges our everyday understanding of reality. In the quantum world, particles like electrons don't behave like the objects we experience in our daily lives. They exist in a haze of probabilities, occupying multiple states simultaneously. This is called superposition. The act of measurement forces these particles to choose a specific state. This is where the many worlds interpretation comes in. It suggests that instead of choosing one state, all possible states occur, but each in a separate, newly born universe. Imagine flipping a coin. In our everyday experience, it lands on either heads or tails, but in the many worlds interpretation, both outcomes occur. The act of the coin landing creates two universes, one where it landed on heads, and another where it landed on tails. This principle, when applied to the vast number of quantum events happening every second, leads to an incomprehensible number of universes constantly branching out. Each universe is as real as the other, forming a complex, interconnected multiverse. Quantum immortality takes this a step further. It postulates that our consciousness, intricately linked to these quantum events, rides this wave of splitting universes, always experiencing a universe where it continues to exist. Section 5. Life, Death, and the Quantum Dance. A new perspective. If the many worlds interpretation holds true, it paints a fascinating, albeit unsettling picture of life and death. Death, in the traditional sense, might not be the end. Instead, our awareness simply shifts to a universe where we continue living. This implies a form of existence that persists indefinitely, branching through the multiverse, experiencing an endless array of possibilities. It's important to note that this interpretation doesn't suggest we become invincible or immortal in any conventional sense. We would still experience life and its challenges, just in a reality where our consciousness persists. Despite its intriguing implications, the many worlds interpretation and consequently, quantum immortality, remain highly controversial within the scientific community. Critics argue that it's an extravagant explanation for quantum phenomena. The lack of any testable predictions makes it difficult to verify or falsify. Many physicists prefer other interpretations of quantum mechanics that don't require the existence of parallel universes. However, proponents of the many worlds interpretation highlight its elegance and internal consistency. They argue that it provides a clean and parsimonious explanation for quantum phenomena, avoiding the need for arbitrary assumptions. The tantalizing concept of quantum immortality, while fascinating, presents a significant challenge. How do you test it? The very nature of the idea, relying on subjective experience in unreachable universes, makes it seemingly impossible to verify scientifically. We cannot interact with or observe these parallel universes. Even if we could, identifying the version of ourselves who supposedly survived a fatal event in another universe would be an immense, if not impossible, task. Furthermore, the ethical implications of any experiment designed to test quantum immortality would be profound and raise questions about the value of life and the nature of consciousness. Despite its lack of scientific verifiability, the concept of quantum immortality continues to captivate the imagination. It offers a glimmer of hope in the face of our inevitable mortality, suggesting that consciousness might not be extinguished, but rather continues on a different path. However, it's crucial to remember that this is just one interpretation of a complex and still developing field of science. It's a thought-provoking idea, but not one to base life decisions on. The true nature of reality, the mysteries of quantum mechanics, and the possibility of a multiverse remain open questions. Further research and theoretical advancements might one day shed light on these profound concepts. Whether quantum immortality proves to be a scientific reality or a captivating thought experiment, it highlights the remarkable nature of the universe we inhabit. It compels us to question our place within the vast cosmic tapestry and the nature of our own existence. The concept of quantum immortality, which suggests that consciousness could continue in a parallel universe after death, challenges our understanding of life and death. The pursuit of understanding these profound concepts is at the heart of scientific exploration. Scientists and researchers dedicate their lives to unraveling these mysteries, driven by an insatiable curiosity and a desire to push the boundaries of human knowledge. While we may never have definitive answers, the journey of seeking knowledge and unraveling the mysteries of the universe is a journey worth taking. Each discovery, no matter how small, adds a piece to the puzzle of our existence and brings us closer to understanding the cosmos. As we continue to probe the depths of quantum mechanics and the potential for parallel universes, we embark on a voyage of discovery that could reshape our understanding of life, death, and the very fabric of reality. This journey is not just about scientific inquiry. It is about the human spirit's relentless quest to explore, understand, and find meaning in the universe.
Quantum immortality. The very phrase hums with an intoxicating blend of scientific intrigue and fantastical speculation. It whispers of a universe where death, the ultimate curtain call, might be nothing more than an illusion. Imagine a reality where consciousness, intertwined with the very fabric of existence, navigates a labyrinth of endless possibilities, always finding a path where life continues. Could this be a glimpse into the true nature of our reality, or merely a seductive siren song of wishful thinking? The allure of immortality is ancient, woven into myths and legends across cultures. From the elixirs of ancient alchemists to the fountain of youth sought by explorers, humanity has always been captivated by the idea of living forever. Yet, quantum immortality offers a distinct flavor, one seasoned with the complex equations and perplexing principles of quantum mechanics. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action spawns a multitude of parallel universes, each with its own version of events. Imagine a maze with countless pathways, each leading to a different outcome. In one path you might meet your end, but in another you continue to thrive. This is the essence of quantum immortality, the idea that there is always a version of you that survives, no matter the odds. But is this tantalizing promise grounded in scientific rigor or merely a fantastical flight of fancy? The concept challenges our very understanding of reality, pushing the boundaries of what we consider possible. The allure of immortality is ancient, woven into myths and legends across cultures. From the elixirs of ancient alchemists to the fountain of youth sought by explorers, humanity has always been captivated by the idea of living forever. Yet, quantum immortality offers a distinct flavor, one seasoned with the complex equations and perplexing principles of quantum mechanics. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action, spawns a multitude of parallel universes, each with its own version of events. It suggests that our understanding of life and death, of beginnings and endings, might be far too simplistic, a mere shadow cast by a far grander, more intricate reality. In this quantum realm, every decision, every action, spawns a multitude of parallel universes, each with its own version of events. But is this tantalizing promise grounded in scientific rigor or merely a fantastical flight of fancy? The concept challenges our very understanding of reality, pushing the boundaries of what we consider possible. To grasp the concept of quantum immortality, we must first venture into the perplexing realm of quantum mechanics. This field, often described as the foundation of modern physics, delves into the behavior of particles at the smallest scales. It's a world where the rules of classical physics no longer apply and where particles can exist in multiple states at once, a phenomenon known as superposition. At its heart lies the many-worlds interpretation, a mind-bending idea proposing that every quantum measurement, every interaction on a subatomic scale, splinters our reality into a multitude of parallel universes. This interpretation, first introduced by physicist Everett in the 1950s, suggests that all possible outcomes of a quantum event actually occur, each in its own separate universe. In each of these branching realities, a different outcome unfolds. Imagine a tree where each branch represents a different possible future. As we move forward in time, we traverse one of these branches, but the other branches still exist, each representing a different version of events. Imagine flipping a coin. In one universe, it lands on heads, in another, tails. This simple act of flipping a coin creates two distinct realities, each as real as the other. The many-worlds interpretation posits that both outcomes occur, each playing out in a separate, self-contained universe. The many-worlds interpretation posits that both outcomes occur, each playing out in a separate, self-contained universe. This means that every decision we make, every random event, creates a new branch in the tree of reality, leading to an ever-expanding multiverse of possibilities. Applied to the concept of death, this interpretation suggests a startling possibility. While in one universe we might succumb to a fatal event, in another, our consciousness persists, having navigated to a world where we survive. This idea, known as quantum immortality, challenges our understanding of life and death, suggesting that our consciousness might continue to exist in a parallel universe where we avoid the fatal event. The allure of quantum immortality, while captivating, must be carefully examined through the lens of scientific scrutiny. This concept, which suggests that consciousness could continue in a parallel universe after death, is fascinating, but remains speculative without solid evidence. At the heart of the scientific method lies a fundamental principle: empirical evidence. This principle demands that any hypothesis or theory must be supported by observable and measurable data. Scientific theories, no matter how elegant or alluring, must find grounding in observable, measurable, and repeatable evidence. This process involves rigorous testing and validation, ensuring that the results can be consistently reproduced. This emphasis on empirical evidence is not a matter of mere academic formality. It's the bedrock upon which our understanding of the universe rests. It is through this meticulous process that we separate fact from fiction and reality from mere speculation. Without verifiable evidence, we drift into the nebulous realm of speculation and conjecture, where any idea, no matter how outlandish, can take root. This is why the scientific community places such a high value on empirical data. The history of science is littered with theories, once widely accepted, that crumbled under the weight of contradictory evidence. From the geocentric model of the universe to the theory of phlogiston, these ideas were eventually discarded as new, more accurate data emerged. This relentless pursuit of truth is what drives scientific progress forward. Herein lies the primary challenge facing the notion of quantum immortality. It remains firmly in the realm of the untestable. The very nature of the many worlds interpretation, while intriguing, presents a seemingly insurmountable barrier to verification. We are, by definition, confined to our own branch of reality. We cannot interact with or observe these parallel universes where our alternate selves supposedly persist. This inability to test or falsify the concept of quantum immortality renders it, at least for now, a philosophical thought experiment rather than a scientifically validated theory. It occupies a tantalizing gray area, a conceptual playground where science and imagination intertwine. Further complicating matters is the enigmatic relationship between quantum mechanics and consciousness. Some proponents of quantum immortality suggest that consciousness plays a role in the selection of which branch of reality we experience. This notion, while captivating, delves into territory where even established science treads cautiously. Consciousness, despite decades of research, remains one of the most profound mysteries of the universe. Its nature, its origins, and its relationship to the physical world are still subjects of intense debate and ongoing research. The very act of observation, of measuring a quantum system, seems to force it from a state of superposition, where it exists in multiple states at once, into a single, definite state. This is often referred to as the measurement problem in quantum mechanics. Whether consciousness plays a role in this collapse, or whether it's governed by other, yet undiscovered mechanisms, is a question at the very frontier of our understanding. Until we unravel the mysteries of consciousness and its potential role in quantum phenomena. The connection between quantum mechanics and immortality will likely remain shrouded in speculation. The challenges in studying quantum immortality highlight a fundamental truth about the scientific endeavor. Testability is paramount. Theories, no matter how elegant or appealing, must be held to the rigorous standard of empirical verification. This commitment to testability is not a limitation but rather the very engine that drives scientific progress. It's what distinguishes scientific knowledge from mere belief or conjecture, while the allure of the unknown will always beckon. It's through the meticulous gathering and interpretation of evidence that we move from the realm of speculation to the solid ground of scientific understanding. So, where does this leave us with quantum immortality? It remains a captivating idea, a tantalizing what if that sparks our imaginations and challenges our understanding of life, death, and the nature of reality itself. However, in the absence of verifiable evidence and with the significant hurdle of testing such a concept, it remains firmly in the realm of speculation. This doesn't invalidate the concept, but it does place it outside the current framework of scientifically validated theories. It serves as a potent reminder that our understanding of the universe is constantly evolving. The story of quantum immortality, then, is not necessarily one of a definitive answer, but rather an ongoing exploration. It's a testament to the power of human curiosity, our relentless drive to explore the boundaries of knowledge and to grapple with the most profound questions of existence. While quantum immortality may never graduate from a captivating concept to a scientifically proven reality, the very act of contemplating it pushes the boundaries of our understanding and fuels the engine of scientific inquiry. And in that journey of exploration, in the relentless pursuit of knowledge, lies a beauty and wonder that transcends any definitive answer. Quantum immortality, a concept both exhilarating and terrifying. It challenges our fundamental understanding of life, death, and the nature of reality itself. Imagine a world where death is not the end, but a doorway to countless possibilities. This is the essence of quantum immortality, a mind-bending concept rooted in the strange and wonderful world of quantum mechanics. At the heart of this idea lies the many worlds interpretation, proposed by physicist Hugh Everett III. MWI suggests that every quantum measurement or event causes the universe to split. Each split creates a new world where a different outcome unfolds. In this grand tapestry of parallel universes, every possibility exists simultaneously. Quantum immortality takes this a step further. It proposes that while we may experience death in one universe, our consciousness persists in another where we survive. This endless cycle of near-death experiences across parallel worlds presents a profound challenge to our perception of mortality and the very fabric of our existence. The implications of quantum immortality are vast and far-reaching, touching upon the realms of physics, philosophy, and even our deepest existential anxieties. It compels us to confront profound questions about the nature of consciousness, the meaning of reality, and the ethical implications of living in a world where death is not the end, but merely a transition. To grasp the concept of quantum immortality, we must first delve into the mind-boggling realm of the many worlds interpretation. This interpretation of quantum mechanics, though controversial, offers a radical departure from our conventional understanding of reality. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once. When we measure a particle's state, the superposition collapses, and we observe only one outcome. MWI posits that this collapse doesn't occur. Instead, the universe branches off, creating separate realities for each possible outcome. Imagine flipping a coin. In MWI, both heads and tails exist simultaneously, each in a different universe. We, the observers, also split, experiencing one outcome in our reality while our other selves experience the alternative. This continuous branching creates an unimaginably vast multiverse, a tapestry woven with every possible quantum event. It's a world where every decision we make, every path we don't take, plays out in a parallel reality. While MWI remains a theoretical framework, it challenges us to expand our view of the cosmos. It suggests that our universe might not be the only one. Instead, we could be part of an infinitely larger and more complex reality than we ever imagined. Central to the concept of quantum immortality is the question of consciousness. How does our awareness, our sense of self, factor into this equation of branching universes? Does consciousness split along with the physical body, or does it somehow transcend the boundaries of individual realities? Some proponents of quantum immortality argue that consciousness is not confined to a single universe. They propose that our awareness, like a wave, might propagate through these branching realities, experiencing a continuous existence even as our physical bodies cease to exist in some timelines. This idea challenges our traditional understanding of the mind-body connection. It suggests that consciousness might not be solely a product of our physical brains, but could be a more fundamental aspect of reality itself. However, the nature of consciousness remains one of the greatest mysteries in science and philosophy. We don't fully understand how consciousness arises from the physical matter of our brains, let alone how it might interact with parallel universes. Despite the lack of definitive answers, the concept of quantum immortality pushes us to confront these profound questions. It forces us to consider the possibility that our consciousness, our very essence, might be far more resilient and interconnected than we ever imagined. The many worlds interpretation, if true, has profound implications for our understanding of reality. It challenges the notion of a single, objective reality and suggests that our universe is just one among an infinite number of parallel worlds. This concept upends our traditional view of cause and effect. If every possible outcome of every event exists in some universe, then does our concept of free will hold any meaning? Are we merely passengers on a predetermined journey through the multiverse? Are choices merely illusions? Philosophically, MWI aligns with modal realism, a view that considers all possible worlds as equally real. This perspective challenges the anthropocentric view of the universe, where our reality is considered the only true reality. However, the vastness and inaccessibility of these parallel worlds raise further questions. If we can't interact with or verify the existence of these other realities, are they truly real, or are they merely theoretical constructs? Despite these uncertainties, the possibility of a multiverse compels us to reconsider our place in the grand scheme of existence. It suggests that our reality, our experiences, might be just a tiny fraction of a much larger and more complex cosmic tapestry. Section 5. Ethical Considerations. Navigating a landscape of infinite choices. The concept of quantum immortality raises ethical dilemmas. If our actions have consequences in parallel universes, how do we navigate this moral landscape? Can we be held accountable for negative outcomes in one universe if there's a positive one in another? Does a positive impact in one universe absolve us of responsibility in another? If death isn't the end, does it diminish life's value in our reality? Does believing in another universe make us less likely to cherish life now? These questions challenge our moral frameworks. They force us to grapple with our actions' cosmic implications. Endless existence raises questions about life's meaning. Does living indefinitely diminish our current life's significance, or does it grant us greater freedom to explore different paths? Section 6. The psychological weight of immortality, a blessing or a curse. While living forever might seem appealing, the reality of quantum immortality could be overwhelming. Imagine experiencing countless near-death experiences and witnessing diverging paths of your life. The knowledge of survival could lead to recklessness or detachment from the present moment. The fear of death might lose its significance, leading to apathy or nihilism. The accumulation of experiences and memories could become an unbearable burden. The sheer volume of information could lead to existential fatigue. Encountering different versions of ourselves raises intriguing psychological questions. How would we react to meeting alternate versions of ourselves? Would we feel a sense of connection or rivalry? The psychological implications of quantum immortality are complex and multifaceted. Endless existence presents profound challenges to our sense of self and our understanding of mortality. Section 7. The paradox of free will. Does choice exist in a predetermined multiverse? The concept of quantum immortality leads us to the debate on free will. If every possible outcome exists in some universe, does free will still make sense? In a multiverse where every possibility is realized, our choices might seem predetermined. If every decision already exists somewhere, what role does our choice play? This deterministic view can be unsettling. It challenges our sense of agency and control. Are we merely actors playing out a script, our choices illusions of free will? Some argue free will can still exist within MWI. Our conscious choices determine which outcomes we experience. Our choices still hold meaning, shaping our journey through the multiverse. The question of free will in quantum immortality remains complex and unresolved. It forces us to grapple with the nature of choice, consciousness, and reality. Section 8. Quantum immortality and the search for meaning. A new perspective on life and death. Quantum immortality, while speculative, offers a unique lens through which to examine the meaning of life and our relationship with death. It challenges our fear of mortality and invites us to consider the possibility of an existence beyond the confines of our current understanding. If death is not the end but a transition to another reality, it could profoundly impact our approach to living. It might encourage us to focus less on fearing death and more on living life to the fullest in the present moment. Furthermore, the concept of experiencing countless lives in parallel universes could provide a sense of comfort and hope. It suggests that even if we face hardship or loss in this life, there are other realities where things might unfold differently. However, this perspective also requires us to confront the potential for existential angst. The sheer vastness of the multiverse and the knowledge that our lives are but a tiny fraction of an infinitely larger reality could be overwhelming. Ultimately, whether quantum immortality provides solace or existential dread depends on our individual perspectives and beliefs. It challenges us to find meaning within the context of a potentially infinite and ever-branching reality. Section 9. The value of speculation. Fueling scientific and philosophical exploration. While quantum immortality remains a theoretical concept, the very act of contemplating such ideas holds immense value. Speculation, even when venturing into the realm of the improbable, plays a crucial role in advancing human knowledge and understanding. By exploring unconventional ideas like quantum immortality, we push the boundaries of our current understanding and open up new avenues for scientific inquiry. These thought experiments, even if they prove to be false, can lead to unexpected discoveries and breakthroughs. Furthermore, philosophical speculation about such concepts challenges our assumptions, broadens our perspectives, and helps us grapple with fundamental questions about the nature of reality, consciousness, and our place in the cosmos. The pursuit of knowledge thrives on curiosity and a willingness to entertain unconventional ideas. While we may never definitively prove or disprove the existence of quantum immortality, the journey of exploring such concepts enriches our understanding of the universe and our place within it. Section 10. Conclusion: Quantum Immortality, a journey into the heart of existence. Quantum immortality, though deeply rooted in theoretical physics, extends far beyond the realm of equations and scientific models. It delves into the very essence of our being, forcing us to confront profound questions about consciousness, reality, and the meaning of existence. Whether or not this concept reflects the true nature of our universe remains to be seen. However, the journey of exploring such ideas is invaluable. It challenges our assumptions, expands our perspectives, and ignites our imagination. Quantum immortality reminds us that we are part of a vast and mysterious cosmos, a universe full of wonder and possibilities that extend far beyond the limits of our current understanding. It encourages us to embrace the unknown, to question our place in the grand scheme of things, and to never stop exploring the infinite frontiers of knowledge and imagination. The quest to unravel the mysteries of quantum immortality is ultimately a journey into the heart of existence itself. It is a journey that challenges us to confront our deepest fears and aspirations, to expand our understanding of the universe, and to embrace the profound beauty and mystery of the cosmos.
A dense fog blankets the street, swallowing sound and light, as if the world has paused its breath. On a cold, moonless night, you step onto the road, unaware of the headlights slicing through the mist. A car surges forward, too fast, too close. Your heart lurches. But before impact, a stranger's hands shoves you aside. You stumble, safe, as tires screech and a body collapses onto the tarmac. An elderly figure, crumpled and still, has traded their life for yours. Later, in the quiet of a police station, an officer hands you an envelope, its edges worn, addressed to you in unfamiliar script. Inside, a note, just 2 words. Study physics. Who wrote it? Why did they save you? The mystery clings like the fog, pulling you toward a life reshaped by those words, toward a destiny entwined with the enigma of time itself. That night lingers, a wound and a gift, as you dedicate yourself to physics, chasing the secrets of the universe. Decades pass, and you stand celebrated, a professor unraveling Albert Einstein's theories of relativity. Time, you learn, is not a straight line but a fabric, woven with possibilities that defy intuition. Your obsession narrows to one question: can we travel through time? In your laboratory, surrounded by humming machines and scribbled equations, you crack it. The world's first time machine glows before you, its soft buzz a siren call. And then, clarity strikes like lightning. You pull the framed note from your wall, the one you've kept all these years, and slip it back into its envelope. Stepping into the machine, you set the dials to that misty night, knowing what you must do. You arrive just in time to push your younger self from the car's path, feeling the impact as the world fades. Your life ends where it was saved. But who wrote the note? It's a question that haunts, a paradox with no clear answer. You carried it back, but you received it first. It exists, creatorless, caught in a loop, a relic that seems to defy origin. This is the bootstrap paradox, a riddle where an object or idea circles through time, its beginning lost in the endless cycle. Did you choose to study physics, or was it always destined? The notes command feels like a whisper from nowhere, a thought born without a thinker. This is the ex nihilo paradox, where ideas emerge without a source. And what of your choice to step into the machine? If you hadn't, you'd have died young, never reaching this moment. Your path seems fixed, unchangeable, a thread in a tapestry already woven. This is the predestination paradox, suggesting your free will is an illusion, your future as set as the past. Imagine time as a river, vast and unyielding, carrying us from the Big Bang's foothills to the universe's distant end. We drift downstream, unable to paddle back or speed forward. Yet the river's source and mouth exist together, unchanging. Yesterday doesn't vanish, just as the riverbed doesn't dissolve behind us. Tomorrow isn't conjured from nothing. It's already there, as real as today. This is the block universe, a concept rooted in Einstein's work, where past, present, and future coexist in a single, four-dimensional tapestry. Your great-grandparents laugh upstream. Your descendants dream downstream, all as real as you are now. This idea, called eternalism, clashes with presentism, the belief that only the present exists, the past gone and the future unborn. Philosophers have wrestled with this since ancient times, but Einstein's relativity gives eternalism weight, painting time as a landscape we traverse, not a fleeting moment. Picture yourself in a canoe, gliding through a jungle river, howler monkeys calling from the trees. The current pulls you forward, no effort needed, but you can't turn back. This is how time feels, relentless, unidirectional. Yet the river's upper reaches don't disappear just because you've passed them. They're still there, out of sight. Similarly, the block universe suggests the past endures, not as memory, but as reality. Einstein's special relativity, published in 1905, shattered the idea of absolute time. There's no universal clock ticking the same for all. Time bends, stretches, depending on how you move through space. One person's now can be another's then. Events shuffling like cards depending on your perspective. If my yesterday is your tomorrow, how can the past simply vanish? It must persist, woven into the fabric of space-time. Space-time, a term coined by Hermann Minkowski in 1908, unites space and time into one entity. Imagine it as a vast sheet stretching across the cosmos, where every event, your birth, your first kiss, your final breath, has a place, marked by 3 spatial coordinates and 1 temporal. A stationary object's mark moves only through time, second by second, tracing a line through this block universe. This line, your world line, maps your journey from cradle to grave. Every particle in your body follows its own world line, weaving together to form you, a knot in space-time's fabric. As you eat, breathe, or age, new particles join, others depart. But your path is fixed, unchangeable. The block universe is like a novel, its pages written, your choices already inked. You can't stray from the plot, just as a train can't leap its tracks. Now consider the paradoxes again. If you're destined to invent the time machine to save your younger self, where does the cycle begin? The letter loops endlessly, but does it age, growing tattered with each pass? This is the restoration paradox, questioning whether objects in a time loop degrade or endure, and what if you hesitate? Could you refuse to step into the machine, letting your younger self die? Logic falters here. If you don't save yourself, you'd never reach this moment to refuse. This is the auto-infanticide paradox, suggesting you can't undo your own existence. These riddles twist the mind, revealing time's complexity. The block universe, with its fixed paths, implies a destiny we can't escape. Yet the idea of looping back to rewrite our story tantalizes, a promise of control over the uncontrollable. Einstein's general relativity, unveiled in 1915, deepened this vision. It describes gravity not as a force, but as space-time's curvature. Picture space-time as a trampoline, sagging under the sun's weight, forming a gravity well. Planets roll through this dip, their paths curved by the fabric's shape. Mercury, closest to the sun, feels this curvature most, its orbit wobbling in ways Newton's laws couldn't explain. In 1859, astronomer Urbain Le Verrier puzzled over Mercury's odd path, suspecting a hidden planet. None was found. Einstein's equations solved the mystery, showing how space-time's curve, not a new planet, caused Mercury's precession. This triumph, announced in a letter to David Hilbert, proved general relativity's power, revealing gravity as geometry, not a pull. Space-time bends, and we move with it, our world lines tracing paths through a universe where all moments coexist. Tests of relativity multiplied. During a 1919 solar eclipse, light from distant stars bent as it passed the sun, confirming space-time's malleability. Gravitational waves, ripples in this fabric, were detected in 2015, further proving Einstein's vision. Black holes, swirling vortexes of curved space-time, bend light and time alike. These discoveries paint a cosmos where past, present, and future sit side by side, a block universe where every event is eternal. But if time is a river and we can't paddle upstream, how do we visit the past? The block universe suggests it's there, as real as now, but reaching it demands bending space-time itself. Your time machine, born from years of study, is the key, but its use raises questions. Did you choose to build it, or was it always meant to be? As you stand before your machine, the note in your pocket, the weight of that misty night presses close. You've lived a life shaped by a stranger's sacrifice, driven by two scrawled words. Now, you understand the stranger was you, older, returning to close the loop, but the paradoxes linger. Who authored your path? Was it ever yours to choose? The block universe holds your story. Every moment fixed, yet the possibility of stepping into the machine, of rewriting a moment, feels like freedom. The river of time flows on, carrying you toward a destiny already written. Yet the chance to loop back, to touch the past, whispers of a universe where endings are beginnings. As you set the dials, the hum of the machine fills the air, and the fog of that long-ago night seems to rise again, waiting for you to step through. The hum of the time machine fades, but its echo lingers in your bones, a reminder of the night you stepped through time to save yourself. Now, standing in the quiet of your laboratory, you wonder, can you truly outrun time, or are you merely chasing its shadow? The block universe holds every moment past, present, future, like stars fixed in a cosmic tapestry. Yet the urge to leap forward, to glimpse tomorrow, burns bright. What would it mean to visit the future, to see the world beyond your years? The river of time carries you forward, its current relentless, like a canoe gliding through a jungle's humid embrace. Howler monkeys calling from distant trees. You can't paddle back, but what if you could speed ahead, skipping decades like stones across water? The idea feels intoxicating, a chance to witness your descendants' lives or the universe's far-off chapters. Einstein's theories, the ones you've spent your life unraveling, suggest it's possible. Special relativity, born in 1905, reshapes time itself. It tells us there's no universal clock, no single now shared by all. Time stretches, contracts. Depending on how fast you move through space, a traveler racing near light speed spends less time in motion, as if hoarding seconds while the world ages swiftly. This is relativistic time dilation, a key to the future. Picture a particle, a muon, born high in Earth's atmosphere, sparked by a cosmic ray's violent collision. These muons, unstable flecks of existence, should decay in a mere 1.56 millionths of a second. Racing at 98% of light speed, they plummet toward the ground. Yet far more reach it than should. Why time slows for them? From their perspective, fewer half-lives pass, as if they're cheating decay itself. In 1938, physicist Bruno Rossi, high in the Rockies at Echo Lake, measured these muons. His instruments, perched 2,300 meters above sea level, captured their strange survival. The muons were time travelers, skipping forward in a way that Rossi's calculations confirmed. Their journey, fleeting yet profound, proved that time bends for those who move fast enough. Imagine yourself as that muon, not falling to Earth, but looping through the cosmos at near-light speed. You embark on a 25-year journey, your spacecraft a speck against the stars. When you return, you're 25 years older, but Earth has aged 125 years. Your friends, your family, are gone, replaced by their grandchildren's grandchildren. The world you knew is a memory, its skyline reshaped, its stories faded. This is no paradox but a fact, woven into relativity's fabric. Time dilation doesn't just bend time, it reshapes lives. Consider the Kelly twins, NASA astronauts, Mark and Scott, born 6 minutes apart. Scott, spending months aboard the International Space Station, moved faster through space-time than Mark. Those extra days in orbit at speeds dwarfing a car's stretched time's flow. Mark, earthbound, aged fractionally more. By their reunion, Mark was 6 minutes and 5 milliseconds older, a gap widened by time's malleability. This effect, though small for astronauts, grows vast at extreme speeds. A traveler at 99.99% of light speed would weigh as much as a rhinoceros, their mass swelling with energy. As Einstein's equation energy equals mass times the speed of light squared reveals. Accelerating them would demand the energy of entire nations, a feat far beyond our grasp today. Yet, even on Earth, time dilation whispers its presence. Climb a mountain, like Rossi did, and you edge out of Earth's gravity well, where space-time is less curved. Time ticks slightly faster there. Atomic clocks, precise to a 15 billionth of a second per year, prove it. In 2022, physicists placed 2 such clocks a mere millimeter apart in height. The higher clock ran faster, its ticks outpacing the lower, confirming gravitational time dilation. Time, it seems, is not just relative to speed, but to gravity's pull. Gravity warps space-time, bending it like a sheet under a heavy stone. Near a massive object, like the sun, space-time curves deeply, forming a gravity well. Planets trace paths through this dip, their orbits shaped by its contours. Mercury, plunging closest to the sun, feels this curvature most, its path wobbling in ways Newton's gravity couldn't predict. In 1859, Urbain Le Verrier puzzled over this, suspecting a hidden planet. None was found. Einstein's General Relativity, published in 1915, solved the riddle. In a letter to David Hilbert, Einstein wrote of deriving Mercury's perihelion motion, a triumph no other theory had achieved. The sun's gravity well, curving space-time, caused Mercury's orbit to precess, proving gravity is not a force, but a geometric dance. This curvature offers another path to the future. Enter a deep gravity well, like that of a supermassive black hole, and time slows for you. Spend a year near its edge, carefully avoiding its pull, and return to find Earth centuries older. This idea, explored in the film Interstellar, hinges on general relativity's truth. Space-time's shape dictates time's flow. Even on Earth, GPS satellites feel this. Orbiting high above, they move faster and sit in a shallower gravity well than we do. Their atomic clocks, ticking at a different rate, must be adjusted to sync with ours. Without this correction, your phone's navigation would falter, lost in time's subtle shifts. These experiments, muons, astronauts, clocks confirm time travel to the future is real, a scientific fact woven into the universe's fabric. But what drives this possibility? The block universe, where all moments coexist, suggests the future is already there, waiting. Your world line, the path you trace through space-time, stretches from birth to death, every choice mapped out. If you could leap forward, you'd land on a page already written, your descendants as real as you are now. The block universe, born from Einstein's relativity, paints time as a landscape, not a fleeting moment. Philosophers call this eternalism, opposing presentism's claim that only now exists. Eternalism sees your great-grandchildren living downstream, as vivid as your ancestors upstream. Time travel to the future, then, is less about creating tomorrow than visiting it, stepping into a moment already etched in space-time's block. Yet, the human cost lingers. To leap forward, you'd leave behind all you know. Imagine returning to a world where your loved ones are dust, their stories faded into history's pages. Ken Liu's story, Memories of My Mother, captures this ache, where a time traveler's journey disrupts family ties, generations slipping out of sync. The future beckons, but it demands sacrifice. You'd need a vessel to rival a muon's speed or a black hole's gravity, feats that dwarf our technology. The energy to propel a human near light speed equals months of global consumption. A barrier as real as the stars. Still, the possibility hums, like your time machine, promising a glimpse of tomorrow's light. As you stand in your laboratory, the note from that misty night in your hand, you feel the weight of time's river. You've saved your younger self, closed the loop. But the future calls, a horizon both distant and near. The block universe holds it all, your past, your now, your yet to come, yet the urge to leap forward, to see what lies beyond, stirs within. The muons, the clocks, the stars all whisper it's possible. Time, bent by speed or gravity, can carry you to a world not yet born. But what would you find there? A new dawn, or a shadow of what you've left? The river flows on, its currents pulling you toward answers that lie just out of reach. In a universe where every moment waits, eternal and alive. The laboratory is silent, save for the faint hum of your time machine, its dials glowing like stars against the dark. You've glimpsed the future's promise, the way time bends under speed or gravity, carrying you to tomorrow's already written. But what of yesterday? Can you step back, not just to save yourself, but to touch the past, to rewrite a moment lost in the river of time? The block universe holds every instant your first breath, a forgotten laugh, the night you were saved etched in space-time's eternal fabric. If the future is reachable, why not the past? The river of time, vast and unyielding, seems to flow one way, carrying you from the Big Bang spark to the universe's quiet end. Yet the past doesn't vanish, just as the river's source remains, hidden beyond the bend. Einstein's relativity, the foundation of your life's work, suggests the past is as real as now, a place you might visit if you could bend the rules of space-time. But how the future yields to speed or gravity's pull. But the past demands something more, a way to tilt the river backward, to paddle upstream against its relentless current. In 1937, a young Dutch physicist, Willem Jacob van Stockham, peered into this possibility. His paper, dryly titled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry," hid a revolutionary idea, Einstein's equations. He showed allow closed time-like curves, paths through space-time that loop back, letting your world line, the thread of your existence, intersect itself at an earlier point. A pensioner could revisit their childhood, or you could return to that misty night, pushing your younger self from harm. On paper, nothing in general relativity forbids this. Your time machine, buzzing in the laboratory, is proof it's possible. But Van Stockham's work hinted at a catch to loop back. You might need to travel faster than light, to step outside your light cone, the boundary of all paths you could take. Imagine standing still, your world line stretching forward through time. Light, racing at 300,000 kilometers per second, sets the limit of where you can go. 1 second from now, you can't be more than 300,000 kilometers away. 2 seconds, 600,000. This boundary forms your light cone, a funnel of possibility widening with time. To reach the past, your world line must curve back, crossing an earlier point. But to do so, you'd need to escape this cone to move faster than light itself. Einstein's special relativity, born in 1905, declares this impossible. The faster you go, the heavier you become. Your mass swelling with energy until accelerating further demands an infinite force. Light speed is the cosmic wall, unbreakable for anything with mass. In 2011, a flicker of hope emerged. Physicists at the Opera experiment, buried beneath Italy's Gran Sasso mountain, announced a shock neutrinos, ghostly particles fired from CERN 730 kilometers away, seemed to arrive 60 nanoseconds too soon. If true, they'd traveled faster than light, shattering Einstein's barrier. The news rippled through the scientific world, promising a path to the past. A neutrino, moving faster than 300,000 kilometers per second, could tilt its world line back, looping through space-time. But by 2012, the dream faded. Faulty equipment, not superluminal speed, explained the anomaly. The light speed wall held firm, closing one door to the past. Yet other paths remained, hidden in space-time's folds. What if you could tilt your light cone without breaking light speed? In 1974, physicist Frank Tipler imagined a way. Picture a cylinder, 10 times the sun's mass, spinning billions of times a minute. Follow a precise spiral around it, and its immense gravity warps space-time, tilting your light cone backward. Your world line, confined within this cone, could loop to an earlier moment, carrying you to the past. Tipler's cylinder, though, was no practical machine. It needed to be infinitely long, a mathematical ideal far from reality. Even a finite version would require vast negative energy, a concept from quantum mechanics where empty space teems with virtual particles, briefly dipping energy below zero. These fleeting bursts, like an overdraft from the universe, couldn't sustain a human-sized time loop. The past, tantalizingly close, remained out of reach. Another possibility emerged, one that didn't demand impossible speeds or infinite cylinders. In 1985, Carl Sagan, crafting his novel Contact, sought a way to send a traveler to the star Vega, 25 light-years away, without breaking light speed. He called physicist Kip Thorne, who suggested a wormhole. Picture space-time as a sheet. Earth at one end, Vega at the other. Fold the sheet, bringing the points together, and a wormhole forms a tunnel through space-time's fabric. Step through, and you're at Vega instantly, without crossing the vast distance. From outside, it looks like faster than light travel, but you've merely taken a shortcut. Thorne realized wormholes could bridge time as well. Drag one mouth of a wormhole on a near light-speed journey, and time dilation slows its clock. Return, and the mouths differ in age. Enter the younger mouth, exit the older, and you're in the past. But wormholes are fragile. Gravity from a passing object could snap them shut. To keep one open, you'd need negative energy again, or perhaps exotic forces like quantum entanglement or magnetic fields. In 1985, Richard Gott and William Hiscock explored cosmic strings, hypothetical threads of immense density left from the universe's birth. Tracing a precise path along two cosmic strings, you could tilt your light cone backward, looping to the past without exceeding light speed. Quantum entanglement, linking particles across vast distances, also hinted at superluminal connections. But transferring data or people this way proved impossible. Each path cylinders, wormholes. Cosmic strings offered theoretical doors to the past, but none were practical. The block universe, with its fixed moments, seemed to taunt you, holding the past just beyond your grasp. Yet the past's allure persists. Imagine stepping through a wormhole, emerging on that misty night, not to save yourself, but to see your parents young, to walk streets long changed. The block universe says those moments exist, as real as now. Your world line, woven through space-time, could loop back, but the paradoxes loom. If you returned and changed the past, would you unravel your present? The bootstrap paradox. Your note. Circling without origin suggests a closed loop. But what if you refuse to write it? The predestination paradox whispers that you can't refuse. Your actions are fixed, written in space-time's book. The auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge free will itself. Was your choice to build the time machine ever yours? The river of time, with its eternal past and future, holds these questions. You've seen the future's possibility, confirmed by muons and clocks. The past, though, demands more a bending of space-time's rules, a tilting of light cones. Van Stockham, Tipler, Thorne, and others map the path, but each requires feats beyond our reach. Infinite cylinders, stable wormholes, cosmic strings. Yet the block universe insists the past is there, waiting. As you stand before your machine, the note in your pocket, you feel the pull of yesterday. Could you step back, not just to close a loop, but to live a moment again? The river flows, its waters holding every memory, every regret. The hum of the machine grows louder, inviting you to chase the past, to seek answers in a universe where time, though fixed, whispers of possibilities yet untraveled. The laboratory air feels heavy, charged with the weight of questions unanswered. Your time machine, its soft glow, a beacon in the dim, hums with the promise of the past, a past you've touched once, saving yourself, but now yearn to explore further. What if you could rewrite a moment, undo a regret, only to find the universe splintering beneath your choice? The river of time, eternal and unyielding, holds every yesterday, but quantum whispers suggest its currents might fork, offering paths where paradoxes dissolve. The block universe, that vast tapestry of space-time where all moments coexist, paints the past as real as the present. You've seen how speed and gravity bend time, letting moons and astronauts slip into the future. The past, though, demands a steeper price, curving space-time's fabric to tilt your light cone backward, looping your world line to an earlier day. Einstein's equations, your life study, allow it through closed time-like curves, paths that circle back like the note you carried to that misty night. But the paradoxes, bootstrap, predestination, auto-infanticide haunt you. If you change the past, do you unravel your now? Quantum mechanics, the strange realm of the subatomic, offers a way out. A vision where time's river splits into countless streams, each a new reality. Picture yourself in a stark room, wrists bound by cold steel, sweat tracing paths down your face. Before you, a glass vial of lethal gas sits beside a hammer, its robotic arm linked to a machine measuring subatomic particles. Each particle can be in one of two states, A or B, a 50-50 chance. If it's A, you live. If B, the hammer falls, the vial shatters, and you die. The machine will measure 100 times before your release. The odds of surviving all 100 are 1 in a million trillion trillion, a number so vast it dwarfs the stars. Your heart pounds as the first measurement clicks. A, you breathe. The second, A again. By the 10th, hope flickers. By the 99th, you're dizzy with disbelief. The final click A, you're free, alive against impossible odds. This is no mere luck. It's a glimpse into the many worlds interpretation, a quantum theory that reshapes time's possibilities. In 1957, physicist Hugh Everett III proposed this idea: every quantum event with multiple outcomes splits the universe. When the machine measures A or B, reality fractures one world where you live, another where you die. After 100 measurements, 100 branches form, and in one, you survive, marveling at your fortune. In 99 others, you perish, each branch a different fate. This is the quantum immortality experiment, a human echo of Schrödinger's cat, where a feline in a box is both alive and dead until observed. Quantum mechanics says the particle exists in a superposition, both A and B, until measured. And so do you, alive and dead until the universe chooses. But Everett's many worlds theory says it doesn't choose. Every outcome happens, each in its own reality. This fracturing universe, a tree of infinite branches, offers a solution to time travel's paradoxes. Consider the grandfather paradox. You travel back. Kill your grandfather as a child, preventing your mother's birth, and thus your own. How? Then, are you here to kill him in the block universe with its fixed world lines? This seems impossible. Stephen Hawking's chronology. Protection conjecture argues the universe forbids such trips, guarding cause and effect. Igor Novikov's self-consistency principle agrees, saying you can visit the past but not change it. Try to shoot your grandfather, and the gun jams, or you miss. Your actions, already written, can't rewrite the page. But these ideas falter in complex cases, like the one posed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser between 2020 and 2022. Imagine a time machine and a set of balls, each either black or white. When two balls meet, they swap colors. A black ball turns white, a white one black. A black ball enters the time machine, emerges in the past, and collides with its earlier self. The collision turns both balls white. The older ball, now white, loops back through the time machine again. But here's the paradox. The same ball exits the same machine at the same moment. Yet it's black the first time and white the second. Novikov's principle can't resolve this. How can the ball be two colors at once? The many worlds theory, though, offers clarity. The black ball starts in time stream A, emerges in time stream B, and collides with its past self. In this new stream, the other ball loops back, not the first. The paradox dissolves because the ball's journey spans different realities, not a single, contradictory loop. This idea frees you from the grandfather paradox. Travel back, kill your grandfather in time stream B, and your existence in time stream A remains untouched. Your mother, your birth, your life all safe in the original stream. Free will returns. You can choose without unraveling your past. The bootstrap paradox. 2 finds an answer. The note you carried to that misty night, seemingly authorless, might originate in another stream. In time stream A, you write it. Travel to time stream B and give it to your younger self. They, in turn, grow up, build the time machine, and carry the note to time stream C. The loop persists, but its origin lies across realities, not in a single, creatorless cycle. The ex nihilo paradox ideas like study physics appearing from nowhere fades as each stream provides a source, a writer in another world. But this solution carries weight. If every quantum event splits reality, the universe fractures endlessly. Every choice, every particle's flicker, spawns new streams. As physicist Bryce DeWitt said, every quantum transition in every star, every galaxy, splits our world into myriad copies, an infinite array of views, each slightly different. Lives every possible life, some where you're a poet, others a president, others never born. John Wheeler, who coined wormhole, grew wary of this, calling it laden with metaphysical baggage. Yet the many worlds theory gains followers, its logic untangling time's knots. Your note, your machine, your choice to save yourself, they ripple across streams. Each reality a new verse in time's endless song. The block universe, with its fixed world lines, seems rigid, yet quantum mechanics suggests flexibility. Closed time-like curves, wormholes, cosmic strings all hint at paths to the past, but they demand exotic conditions, negative energy. Infinite cylinders, or stable tunnels through space-time. Quantum entanglement, linking particles across vast distances. Teases superluminal connections, but data can't travel that way. Still, the many worlds theory softens these barriers. If you step through a wormhole to the past, you emerge in a new stream, free to act without breaking your origin. The river of time, once a single flow, becomes a delta, its waters splitting into countless channels, each holding a different story. As you stand before your time machine, the note in your pocket feels heavier, its words a bridge between worlds. You've saved yourself once, closing a loop, but the past calls again, not just to repeat, but to explore. Could you visit a lost moment, see a loved one smile, without shattering your now? The many worlds theory whispers yes, offering a universe where every choice branches, where paradoxes dissolve into new realities. The laboratory's hum grows louder, the dials glowing with possibility. Time's river, vast and eternal, splits before you, its streams shimmering with lives unlived, moments unmade. You step closer, drawn to the promise of yesterday, wondering which world awaits your next leap. The glow of the time machine flickers in the laboratory, a silent witness to your journey through time's vast river. You've chased the future, glimpsed the past, and felt the universe splinter into countless streams, each holding a version of you. Now, standing at the edge of this moment, you wonder, what does it mean to live in a cosmos where every instant is eternal, where every choice echoes across realities? The note in your pocket, worn by years and loops, whispers the answer. Time is both your cage and your freedom. The block universe, that four-dimensional tapestry where past, present, and future coexist, holds your life's story, from the misty night you were saved to the hum of the machine before you. Einstein's relativity, your life's work, reveals time as a landscape, not a fleeting moment. Your world line, the path tracing your existence, weaves through this landscape, fixed yet full of possibility. You've seen how speed and gravity stretch time, letting muons and astronauts slip into the future. You've explored paths to the past, closed time-like curves, wormholes, cosmic strings, each a theoretical bridge to yesterdays as real as now. The many worlds theory, with its branching realities, untangles paradoxes, letting you rewrite moments without unraveling your origin. But what does this mean for you? A knot of world lanes navigating an eternal cosmos. Picture the river of time, its currents carrying you from the Big Bang spark to the universe's distant end. You're in a canoe, gliding through a jungle's humid embrace, howler monkeys calling from unseen trees. The river's source, its bends, its estuary, all exist together, unchanging. Your great-grandparents laugh upstream. Your descendants dream downstream, each as vivid as you are now. This is eternalism, the idea that all moments are equally real, opposing presentism's claim that only now exists. Philosophers like St. Augustine, in the 4th century, saw the present as a knife's edge between a lost past and an unborn future, but Einstein's general relativity, unveiled in 1915, paints a different picture. Time and space, woven into space-time, bend under gravity's weight, forming a block universe where every event, your birth, your choices, your end, is already written. Your world line, a thread in this tapestry, maps every step, from the breakfast you'll eat tomorrow to the day you'll marry. Every action is etched, unchangeable. The block universe is a book, its pages fixed, your choices pre-written. The note you carried back to that misty night, saving your younger self, was always part of the story. You didn't choose to study physics. The note, looping through time, ensured it. This is the predestination paradox, suggesting free will is an illusion. You built the time machine because you had to, because an older you already saved the younger, closing a loop that never began. The bootstrap paradox haunts you too. The note, creatorless, circles endlessly. Its origin lost in the river's flow. Does it age, growing tattered with each loop? The restoration paradox asks this, while the auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge the very notion of choice. Yet, the many worlds theory offers freedom. Each quantum event, each flicker of a particle, splits reality into streams. In one, you wrote the note. In another, you received it. In one, you saved yourself. In another, you hesitated. The grandfather paradox dissolves. You can kill your grandfather in a new stream, leaving your origin untouched. The ex nihilo paradox fades. The idea to study physics has a source across realities. Your time machine, buzzing before you, could carry you to a new stream, where choices reshape outcomes. But this freedom comes at a cost. As physicist Bryce DeWitt said, every quantum transition, in every star and galaxy, splits our world into myriad copies. An infinite array of you's lives, every possible life, some triumphant, some tragic, some never born. John Wheeler, who named the wormhole, called this metaphysical baggage, yet its logic untangles time's knots. The river of time, once a single flow, becomes a delta, its waters branching into countless channels. You're not just a passenger, but a chorus of selves, each singing a different verse. Time travel to the future, proven by muons and atomic clocks, is a fact. Astronauts like Scott Kelly, aging fractionally less than his twin, confirm it. GPS satellites, ticking faster in Earth's shallow gravity well, rely on it. The past, though, is less certain. Closed time-like curves, like those Van Stockham proposed in 1937, allow it on paper. Wormholes, suggested by Kip Thorne for Carl Sagan's Contact, offer shortcuts through space-time's folded sheet. Cosmic strings, imagined by J. Richard Gott, tilt light cones backward, but each demands exotic conditions, negative energy, infinite structures, or stable tunnels beyond our grasp. Quantum mechanics, with its virtual particles and fleeting negative energy, hints at microscopic time loops, but scaling them for a human remains a dream. Still, the past feels close. You've touched it once, saving yourself, but the urge to return persists. Imagine stepping through a wormhole, not to that misty night, but to a quieter moment, a childhood afternoon. Your mother's laugh, a world before loss. The block universe says it's there, as real as now. But the paradoxes linger. If you change a moment, do you split the universe, creating a new stream? The many worlds theory says yes, freeing you to act without breaking your past. Yet, each action spawns new realities, an infinite cascade of yous. The note in your pocket, its ink faded, feels like a relic from another stream, a message from a self you'll never meet. Was it ever your choice to follow it, or was it written in the stars? Time travel, whether forward or back, reshapes not just moments, but meaning. To leap forward, you'd leave loved ones behind, as Ken Liu's Memories of My Mother shows, where a traveler's journey fractures family ties. To visit the past, you'd risk splintering reality. Each choice a new world. The block universe, with its fixed world lines, suggests you're a character in a finished book. Yet quantum mechanics offers a multiverse where every page branches. Your time machine, a bridge between these truths, hums with possibility. You've lived its proof, saving yourself, but the cost weighs heavy. Each trip, each loop, echoes across streams, reshaping who you are. The river of time, eternal and vast, holds every version of you, past, present, future, each a knot in space-time's wave, unraveling and reforming with every choice. As you stand before the machine, its glow soft against the laboratory's shadows, you feel the river's pull. The note, tucked in your pocket, is both anchor and sail. You've traveled its loop, closed its circle, but the universe is wider now. Its streams infinite. Time travel, once a dream, is your reality. Yet it asks more than it answers. Are you free or fated? Do you write your story or merely read it? The block universe holds every moment, every you, in its embrace. The many worlds theory offers countless paths, each a life unlived. As the machine's hum fades, you step back. The note's words study physics echoing in your heart. Time's river flows on, its waters shimmering with every possibility, every regret, every hope, leaving you in awe of a cosmos where all moments, all selves, are eternal.